Let's do chapter 15.2 for the topic simple harmonic motion. I've already defined it in 15.1 as as a type of oscillation that contains a restoring force. Now we are going to give a more technical definition in terms of calculations. Okay, so a simple harmonic motion is simple. A periodic motion is a periodic motion where displacement is a periodic motion where displacement versus time is a sine wave. Okay, so what this means is that the type of motion that we are looking at under the simple harmonic motion, their relationship is represented by a sine wave that is also referred to as a sinusoidal curve. Okay, this is not different from a sine graph that you know from mathematics. So that graph is the one that is used to represent simple harmonic motion. So this is one of the definitions for simple harmonic motion. Okay, so the word harmonic itself, it originates from music. Okay, when they are saying musical harmonics. Okay, so this is what simple harmonic motion means. Okay, so we've already defined it that it contains a restoring force. So this restoring force is directly proportional to the displacement from equilibrium. Okay, so this restoring force, one thing that you have to know, I will give an example shortly with a spring. Okay, is that it is directly proportional to the displacement. Okay, is directly proportional to the displacement from the equilibrium. Okay, and one thing about the direction of the restoring force is that it always points towards the equilibrium. Okay, so the restoring force is directly proportional to the displacement from equilibrium and always points towards the equilibrium. Okay, and always points towards the equilibrium. Let me give an example with the oscillation of a spring and always points towards the equilibrium. If you have a spring with a mass, okay, suppose that the spring was stretched, okay, and the equilibrium is somewhere here. Okay, so if this spring is stretched to the right, the restoring force is to the left towards the equilibrium, which is what I was mentioning. So the more you increase the distance, the more the restoring force. Okay, this is what really means. And then suppose that the spring is now stretched, is now compressed to the left. Here's our spring being compressed to the left. What is happening is that now our restoring force, suppose that the equilibrium position is still around here. What is happening once again is that our restoring force is directed to the right, now towards the equilibrium position. Okay, and this motion is sinusoidal, okay, which is why we represent it with a sine wave. Okay, so the next thing we're going to talk about the property of a simple harmonic motion, which is referred to as the isochronous motion. Okay, what does this term mean? This term is simple, tells you that period in simple harmonic motion is independent of the amplitude. Okay, it tells you that uh, period in simple harmonic motion is independent of amplitude. Okay, we have seen the term isochronous motion, and then we have stated that the period is independent of amplitude. But what does this really mean? Let's look at it in terms of a graph involving two objects with different amplitude. Okay, I'm just going to quickly sketch a graph. Okay, suppose I have object 1 that is having um, a longer amplitude. Suppose this object is having an amplitude A, okay, and then we have another object that is having an amplitude that is less than this one. Something like this. Um, the second object has a smaller amplitude than the latter object, but look at the time. Suppose that this is 40. You can see that they traveled at the same time. So this is what we call simple harmonic motion. So if you look at object A, is the one that I indicated in object 1. Let me call it object 1, the one that I indicated in red, and then call this one object 2. Okay, its amplitude is half of the one for object 1. Okay, you can see that the amplitude for object A is less than the amplitude for is lower than the amplitude for object 2, but then they are moving at the same time. Okay, which is why we are saying period is independent of the amplitude, because no matter how large the amplitude of object can be, it will still move at the same time as any object that has a smaller amplitude. Okay, so this is an important property for simple harmonic motion. It is going to apply in some of the calculations that are going to appear under this question. Okay, so let's go and look again at the relationship between Um, Displacement. Most of you are familiar with the relationship between displacement, velocity, and acceleration. In Most of you are familiar with this topic in linear motion, but now we are dealing with the simple harmonic motion. How will these three quantities relate? Okay, so we have already stated that we can have two objects that have different amplitude, but um, but with the same period. Okay, two objects can have different amplitude. Two objects can have different amplitude, but with the same period. Okay, but with the same period. So now, um, consider to fully explain the relationship between these three quantities. Consider a pendulum. Consider a pendulum bob that is moving in circular motion around a circle. I'm going to draw my circle. This pendulum is moving in circular motion, okay? And then what is happening is that on the right, we are going to put a shadow. We're going to put a screen that is going to trace the shadow of this pendulum, okay? So this represent a screen over here that is tracking the shadow of this pendulum that is moving around a circle. It is being tied there. At the end, it's being tied there, and then it is moving in a circular motion. Okay, so what is going to be happening on the shadow in the screen here is that we are going to have its shadow. Suppose that when it is at this position, its shadow is here. When suppose that now it moves down, its shadow there is going to move with it and come down on the screen there. Okay, so this distance from here to here um, will be represented by the equation A sine of omega t. You already know that A represents the amplitude and omega represent the angular frequency. Okay, so A is the amplitude, okay, of your pendulum, and then the omega is the angular frequency or the angular speed. Okay, so and t is for time. So this is an example of simple harmonic motion. Okay, so and then you know that there is an angle which is, you can use theta or phi. Okay, so this angle here is represented by omega t. So in this equation here, you can replace it with theta there, and you know the amplitude that is being referred to in the equation is A, which is the length of the string that is holding the bob. Okay, so basically this is an example of simple harmonic motion. Okay, um, so you remember when above here I said I'm going to introduce the relationship between displacement, velocity, and acceleration, and already I've defined the position here as the multiplication of the amplitude and the sine of omega t. Okay, so what is happening now? We have to derive the formula for velocity and acceleration. Okay, so we have already defined our position as sine of t omega. Yeah, so how can we find the velocity when I have to derive it? Okay, if we say derivative of the position over there, we are going to get a omega sine of omega t. So this will be the expression for our velocity. Okay, this will be the expression for our velocity. So we can see the relationship between the velocity and the amplitude. They are also directly proportional, as I've mentioned above. And then we can go ahead once again to find the expression for the acceleration, okay, which is the derivative of the velocity given by negative omega squared. Um, I made a mistake here. The derivative of sine is cos of omega t. So when we move ahead here, the derivative of cos is going to be negative sine. Okay, so this is giving us the acceleration. This is giving us the acceleration of an object that is moving in simple harmonic motion. Okay, so we can already observe and compare, right? You can see that amplitude is directly proportional to the acceleration again. Okay, so I introduced to you above what is being referred to as the restoring force. Okay, I introduced to you what is called the restoring force. Now, what is the relationship of this restoring force with the position? Okay, I've already mentioned that the restoring force always points towards the equilibrium. Okay, the restoring force always points towards the equilibrium. So now what will be its relationship with the position of an object? Okay, its relationship is given by f is equals to negative k x, okay, in which f is the restoring force, okay, k is the spring constant, and then x is the position of an object, okay, and then when I have x, which is the position, The negative sign comes from the fact that the force is opposite from the displacement. Okay, I've already explained above that the force is opposite to the displacement. Okay, this is basically Hooke's law for a spring, but it applies to simple harmonic motion. Okay, so in simple harmonic motion, the restoring force is directly proportional to the displacement as shown.